This is AP Calculus AB, and in this video, I'm going to talk about section 8.1 again, integral as net change. And this is really just a little bit of an extension of what I covered in the last video. So in the last video, we started talking about the idea that if we integrate a rate function, we get the net change in whatever that rate is measuring. So we're going to look at just a couple of different examples today, just so you can get a feel for the fact that even though we're primarily talking about integrals and a lot of stuff where we're doing integrals with a calculator, doesn't necessarily mean that every time we see one of these, we're actually going to solve an integral. And so for an example, what I have here is an approximation of an integral. So we've got a trapezoidal rule question. So this is actually from your textbook, and same idea as what we were doing before. We're looking at a rate function and we're trying to integrate our rate function. But this time, since we don't have the function, we just have values for the rate function, we're going to have to do an approximation method. So it says a pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour as shown in table 7.1, which is shown below. How many gallons were pumped during that hour? Okay, so this is actually fairly simple as long as you remember what we did with trapezoidal approximation, and it's been several weeks on that. So, and we haven't really used it since then. So I wanted to make sure that we discuss how we would do a problem like this. So remember, in the end, we're still trying to do the same thing that I talked about in the first part of section 8.1. We're still trying to think about integrating this rate function, in this case from 0 to 60 minutes. I would want to integrate r of t dt. But like I said before, the problem is we don't have a rate function. So all we have are values at different points in time. So what I'm going to do here now instead is I'm going to do a trapezoidal approximation. We talked about before why trapezoidal approximation is the best method we have available to us when we have a table of values, because it's going to use all of our data points. And so we're going to get all of the possible information incorporated into our approximation. So for this one, we do have time intervals that are all equally spaced at 5-minute time intervals. So to evaluate this is actually fairly simple. So remember, when we do this, we have our h divided by 2, where h is going to be the length of the subinterval. That's going to be 5 minutes. So I have 5 over 2. And then I just have to multiply by, and remember, when I do this, the first and last terms in my table are used once because they appear in one trapezoid. All the terms in the middle are going to be used twice because they show up in 2 trapezoids. So essentially, I've got 58 plus 2 multiplied 2, and then I have all these values in the middle, 60 plus 65 plus, and I'm going to have to use another line here, 64, and so on. Now, ideally, you would write all of these out, but we've got 64, and then we're going to go to, let's see, I'm going to jump down below here, all the way down to that 63 that we have, the second to last number. And then the last term was also a 63, and that's there one time. Okay, so that's my approximation. Now, ideally, you would write out all of the terms. I'm just trying to make this a little more concise. And then we just plug this into the calculator. So our total, which is going to be the amount that was pumped, would be approximately 3,582.5 gallons. Okay, so still the same idea, integrating the rate function to get the net change. In this case, again, we're just approximating the integral, but it's still the same concept. Okay, so the other example that I wanted to show you here has to do with what we call Hooke's law. And a lot of you have seen this in physics before, probably not from the perspective of using an integral to solve for Hooke's law. But what we're looking at here with Hooke's law is we're talking about a spring being stretched or compressed. And you might not think that this is a rate function, but it still kind of works out in the same way as integrating a rate function. So when we do Hooke's law, the relationship that we have is the force that it takes to stretch or compress a spring is equal to kx, where k is what we call our spring constant. X is the distance that we are from what we call our natural length, which is like our 0 position. So the natural length is just, if you just put the spring down and didn't touch it, what's the length of the spring? And then to either stretch it or compress it, it's going to take a certain amount of force. Okay, so we know that in this problem, it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. So 10 newtons is a force. So I know it takes 10 newtons to stretch this spring 2 meters beyond its natural length. And what that tells me is that this spring constant is going to be 5. Okay, so in the end, I have a force function here. My f of x is equal to 5x. Okay, so that's my force function. Now, when we calculate work, the question says how much work is done in stretching the spring 4 meters from its natural length. When we calculate work, a lot of you already know this, but work is equal to force multiplied by distance. So I've got my force multiplied to my distance. Now, when you saw this in your physics classes, most likely you just had a fixed force, a force that was constant. And so then you just did force times distance, and that gave you the amount of work. Well, what we have here is we have a variable force. So you can kind of think of that force as a rate function. When we calculate the work then, that's going to give me an integral that I'm going to solve because I want to do force times distance. And what we're going to do is we're going to treat force as a constant over a tiny interval dx. So what my integral is doing is adding up all of those small pieces of work. So in the end, I can solve this integral out, and I get work is equal to 40 Newton meters, which is the same as 40 joules. Okay, so these are fairly simple questions, but the main thing is you have to find the force function, and then in the end, you kind of treat that as your rate function.